All right, welcome everybody to a new edition of NEXTEpisode, the podcast that talks about sustainable technology solutions. Today we're going to talk about hydrogen, which is the most abundant element in the universe, also very simple, H2. And it's a crucial element, a crucial molecule to decarbonize the industry. I'm definitely not an expert in this field, so I've asked Cristina Guazzotti to join us. Welcome, Cristina.
Thank you.
You are the head of technology solutions at KT Tech.
Yeah.
Can you maybe share a bit about your background before we dive into the hydrogen world?
Yeah, okay. Thank you, Mark. And I'm the head of technology solutions in KT Tech. And I'm here invited to speak about hydrogen, I think because I'm almost spent all my career on hydrogen field and technologies. I started working almost 30 years ago in KTI at the time. My background, educational background, is chemical engineering, but I started in KTI, and most of this period has been spent on the technology relevant to hydrogen.
Okay.
And now I'm responsible for all the technology that are part of the portfolio in KT Tech. That one is one of the company of NextGen Group.
Okay.
And most of this technology are relevant to hydrogen.
Okay.
Maybe this.
That's a good start. So hydrogen, I think, is has been around here. Comes naturally in the sun.
Yeah.
I think on Earth it's more difficult to extract. Yeah. If I'm correct, it comes from natural gas and then it's reformed.
Yeah. Exactly.
I think we've let's say industry is a decades old technology. So hydrogen has been made for a very long time.
Absolutely.
Of course, with the transition towards renewable energies, I think we see a shift towards more low carbon hydrogen.
Yeah.
How does that work? What's the other different technologies, or is it the same technology that has been adapted, or what are the flavors of, let's say, hydrogen technologies?
Yeah. In the time, in this period, hydrogen usage has been switched, remain mainly as a desulfurization agent in the refinery, or used for producing from petrol, from heavier hydrocarbon, smaller hydrocarbon. Now it's more moved to the decarbonization or a vector, an energy source, an energy vector, really, because it's not a source of energy for automotive.
Okay.
So the hydrogen, let's say, usage over the time, over this period in my career, has been changed. Okay. And now, for sure, and the technology that are linked to hydrogen production has followed this also this path.
Okay.
Because in the beginning, in the original, when I started to work, there was mainly what now is named grey hydrogen.
Yeah.
Means production of hydrogen from hydrocarbon using steam over a catalyst bed. But there was no, let's say, specific focus on the amount of CO2 that was produced by this process.
Okay.
Because this is an endothermic reaction, means that need heat from external source to take place over this catalyst. And this was performed using furnaces, that is the steam method reforming furnaces.
Yeah.
And means that there are flames inside, there are burners that are burning fuel gas or methane, and this produces CO2. And this CO2 through the stack is emitted to the atmosphere. At that time, there was nobody took care about this. And what was important is to produce hydrogen for need in the refinery or in the chemical industry.
Okay.
then now there is a new path, new process that are asking to produce hydrogen, but looking at technologies or solution that reduce the CO2 emitted to the atmosphere.
So that's a adaptation of the steam methane reforming, or is it something completely new?
Both. I mean, the steam reformer solution, the SMR, can be adapted to reduce the amount of CO2.
Okay.
I mean, for example, can be designed in order to burn partially or totally hydrogen, for example. So produce more hydrogen that is sent back to the furnaces. And this will reduce the CO2 because when you burn hydrogen, you produce water and not CO2. Or can be adapted in order to achieve what is named blue hydrogen by removing the CO2 and collecting this to be stored in specific areas. This is the way that normally is applied to decarbonize the process. So capture the CO2 and let's say store it
store it underground somewhere.
Underground somewhere. So this makes this process and the product as well, the hydrogen, blue. So this is the same SMR that is modified to produce this.
Or modern SMR.
Modern SMR. Or we can use different technology that apply different concept. One is the ATR, autothermal reforming, and the other one is the CPO, that is catalytic partial oxidation. Are two technologies that are part of our portfolio.
Okay.
And these are a sort of, different concept because the heat that is needed to have this reaction is not produced by this burner that are external, to the catalytic bed, but is something totally integrated. Okay. So the oxygen that is used in the ATR, autothermal reforming, is burning, the hydrocarbon, and the heat that is provided by this reaction, by this mixture, within a flame, is the one that provided to this equipment in which is also installed the catalyst bed, enough heat to produce hydrogen, so to transform the hydrocarbon in hydrogen. What is the advantage? That there is no furnaces. This is a vessel. Let's imagine as a vessel that need also only a small heater in front to preheat the mixture that is introduced in this vessel. So starting from the SMR, we have a smaller heater in front, means we have less emission of CO2 to the atmosphere. Okay. The further step of decarbonization, reduction of CO2, is use the catalytic partial oxidation, the CPO. That is another technology part of our portfolio, in which there is no burner. So, the heat needed to have the reaction over the catalyst bed is produced by the contact, the mixture of oxygen and the hydrocarbon over a very active bed of catalyst that is auto-producing the heat needed to have this reaction. And this means that we don't need even the furnace in front to preheat this mixture. And this will reduce further the CO2 emission to the atmosphere. So, as you see, is a sort of step of improvement that can be done on the SMR modifying heat or changing totally the technology.
It sounds like you're going to reduce or remove the furnace. So does that also mean that the investment, the capex is reduced?
As well, depending But there are other factors that are linked to the capacity.
Okay.
So because this technology cannot be applied on complete range of capacities, and so means that there are areas or segment of capacity application in which each technology is the best solution to be applied.
Okay. Can you give a range for each of the technologies? What sort of what's the max capacity?
The CPO, the catalytic partial oxidation, is the solution we use to small up to medium size range. Means generally up to 50,000 normal cubic meter per hour of hydrogen production or equivalent hydrogen production. Then there is the steam methane reformer, the SMR, that can range for small capacity up to around 200,000 normal cubic meter per hour.
Okay.
So it's feasible technically, but the best is 115,000 normal cubic meter per hour. 150,000 normal cubic meter per hour. And then for higher capacity is for sure the ATR, the technology to be applied.
Is there a max limit to the ATR technology?
Really can be very big, also because the technology we apply is mainly tailored on that, having the possibility to increase a lot the production of hydrogen also as a front end, because it's a typical technology solution to produce a syngas, because the syngas is really the result of the reaction I described before.
Yep.
Then this mixture of hydrogen, CO2, CO is purified to have only hydrogen at a very high purity, 99.999, whatever is needed. But this mixture, if it's not, let's say, purified to produce hydrogen, is the precursor, what is before, other step, like production of ammonia or production of methanol. And for such a kind of product, generally the amount of syngas to be produced is huge. Yep. So the ATR is the solution to be applied.
Okay. So
can arrive up to 600,000 normal cubic meter per hour. Okay. So a lot is a hydrogen equivalent.
Okay. And then in terms of the, let's say, carbon intensity, of course, the steam methane reformer has got the biggest, especially if you don't have any carbon capture.
As the higher carbon footprint, yes. Yeah. Yes.
So it sounds like the CPO technology is the most blue, but has a lower capacity, a lower max capacity.
Yeah.
But what's the difference between let's say the CPO technology and the ATR, because I think both can have the carbon capture, both are in let's say low carbon direction.
Yeah.
Why would I choose if I have what's the minimum capacity of the ATR technology?
The ATR is overlapping the SMR capacity, so becomes convenient at around 200,000 normal cubic meter. So
it's really ranges overlap from CPO to SMR to ATR.
To ATR, yes. And the main difference in terms of carbon intensity between the CPO and the ATR is this furnace is in front. That for the CPO is not needed. So this makes the CPO solution suitable when is needed a very, very, very low carbon intensity of the process.
And then KT Tech has done a lot of SMR plants so far. You've got, I think, 60, 70 reference plants.
Yeah.
To what extent is it possible to revamp existing plants to be more sustainable, to decrease the carbon intensity? Yeah,
it's always possible to decarbonize a gray hydrogen production plant. So because can be, let's say, introduced the carbon capture on the process or on the flue gases.
Okay.
but generally this is something that can be done. Sometimes the problem linked to that is that existing plants are on, let's say, not on greenfield, but on brownfield. So is to add these units of that provide this carbon capture require some plot area to be available nearby to capture, for example, from the flue gas, and this is sometimes not easy. So it's feasible, can be done. We do this when it's needed, but it may be not easy to perform.
Do you see differences in, let's say, regions where one region is more interested in decarbonizing and another is more just focused on capacity, or is the trend globally more or less the same?
The trend is globally the same almost. Of course, Europe is the area where the decarbonization is more, let's say, important, mainly to produce blue hydrogen, while in other countries where there is more, let's say, fuel available, for example, the solution moving to the green is easier to do. Because there are lands available than in Europe. But for sure, Europe is where the solution of decarbonization is more requested at the moment.
Okay. And then I think also a different technology is the e-blue, which I think we have not talked about yet.
Yes.
Can you dive a bit deeper in that part?
Yeah. Right. The e-blue is what we can consider in some way the bridge between the blue and green hydrogen.
Okay.
Because is an SMR in which the external heat that is conventionally provided by fuel and burners is provided by power, by the electricity.
Yeah.
So it's an electrified steam methane reformer. That means this will not have any stock. And the solution, the process solution we have identified, make possible a complete electrification of the process.
Okay.
And this, of course, when you have a green power source, this will make this even really let's say effective in terms of carbon intensity. This application has also a limit in capacity, at least in a single line, and that can be identified around 10,000 normal cubic meter per hour, 15,000 normal cubic meter per hour.
So it's small scale, but
small scale, but
very blue.
Yeah. Absolutely.
Yeah.
Also because when you have maybe in such a capacity is really easy to apply when you have biogas, so means methane from biological source. This is perfect because at the end you will be totally neutral based on CO2 emission.
Okay. So, and then let's say downstream of the hydrogen, you've already touched briefly upon ammonia, but what's the use of hydrogen in the sense? What are the, let's say, the main outlets for technology? Yeah.
So the hydrogen generally is an utility within the refinery. So it's used for the desulfurization of process of hydrotreating of heavy hydrocarbon to produce smaller hydrocarbon. I mean. And this is the main usage in the refinery. Then there is the use of hydrogen to produce chemicals like ammonia, for example, and then ammonia can be used to produce urea. Because for example, when you have hydrogen and you want to make the hydrogen production blue, you have to capture the CO2. And one of the important integration that we are doing also within NEXTChem group, because we have other company part of the group that are taking care of ammonia and urea production, carbon, and this CO2 that is captured from the hydrogen, and the hydrogen is used to produce ammonia, the CO2 that is captured is used to produce the urea.
Okay.
So it is a totally integrated process, end to end, from the hydrogen production up to the urea.
Okay, so it's need hydrogen, ammonia, urea, and then even also nitrates, I think, and
also nitrate.
And methanol, I think, also is a
then
different
methanol
route.
also is the same, because all the process I described, all the technology I described, SMR, CPO, ATR, and ESMR at least, the result of the reaction is what is named syngas. So it's a mixture of hydrogen, CO2, and CO maybe, and some slip of methane. This syngas, to produce hydrogen, needs to be purified. I mean, the hydrogen needs to be separated is physically separated by this. And if not, this syngas is the precursor, is what is needed to produce methanol. And also, as a part of our Next, there is a company like GasConTech that is the one that is leading the methanol production. So also in this case, we can provide a full, package, full proposition to produce also methanol.
And then you also have, of course, not part of NextChem, but part of MAIRE Group, also the E&C business that can also build all of these technologies. So
absolutely,
you really have the full integrated package.
In fact, this is what we can do, because now we are a technology part, the technology arm of MAIRE Group, but of course we can execute a project up to the execution, taking the advantage of having part of the MAIRE Group, also the company in the E&C part, as KT and Technimont.
Okay, well, thank you so much. I think that gives a lot of, let's say, ammunition for also for future episodes of this podcast. A lot of topics to talk about: ammonia, urea, methanol integration, project development. So,
I think we are an interesting group.
Yes, for sure. So I'd like to thank you so much, Cristina, for sharing your insights in hydrogen. It's much appreciated. Also, a big thank you to our listeners. If you're interested in these type of podcasts, also on different technologies, please subscribe. And we love to hear your feedback either via LinkedIn or in the comments on the platform that you listen to this podcast. Thank you so much, and I hope to hear you at the next episode. Thank you.